So we'll start our study of AP biology with the structure of water and the different types of chemical bonds. Unit 1 has 6 chapters, and as you know, there are 8 units in AP biology. And this first unit lays the foundation for a molecular foundation for how everything else operates at a bigger level. In Unit 1, Chapter 1, we will study the structure of water and the different types of bonds. And in Chapter 2, we will look at the different elements that make life: carbon, hydrogen, oxygen, nitrogen, and sulfur. And in the next 3 units, we will look at macromolecules, which are large molecules, and they are carbohydrates, lipids, proteins, and nucleic acids. We will look at how the structure determines function in these biological macromolecules. And finally, we will spotlight in the last chapter here, we will spotlight on nucleic acids. So the learning objectives for this chapter, we are going to start looking at different types of chemical bonds, and we'll also look at polar versus non-polar molecules, and we will look at the bonds that make the chemical bonds that make water, and how the different chemical bonds in water contribute to its properties, including cohesion, adhesion, specific heat, latent heat of vaporization, and surface tension. And finally, we'll look briefly at pH, because this is an important concept that will keep showing up throughout your course. So there is a hierarchical arrangement of material in biology. Atoms, as you know, are made of protons, electrons, and neutrons. And as you know, the center of an atom is the nucleus, which contains the protons and the neutrons packed together. And protons are positively charged, neutrons are neutral charge, which is no charge. And then the electrons are distributed in the space called an electron cloud around the nucleus. And so atoms come together to form molecules and compounds, and then they organize into organelles, which are subcellular structures that come together to make a cell. And the cell is the fundamental living unit of an organism. In a multicellular organism, cells come together to form tissues. Tissues create organs. Organs create organ systems by working with other organs. And then finally, it results in an organism. So what are chemical bonds? Chemical bonds are the forces that hold atoms together in compounds and molecules. So we have an atom, we have another atom, and these two atoms come together to create a molecule. And they are trying to, both of these atoms are trying to come to a stable configuration as far as electrons go. And they can do that by sharing or losing or gaining electrons. And when they do that, they come to a state of stability. And that interaction that's created by sharing or losing or gaining electrons is called as a chemical bond. One of the fundamental things you need to know about chemical bonds is the idea of valence electrons and the octet rule. Valence electrons are the electrons in the outermost shell of an atom. So if you think of the electrons being distributed in specific areas around the nucleus, and the outermost space in which the electron is present is the outermost shell, or the outermost orbital, and the outermost orbit. And so the electrons present in that outermost orbit are called as valence electrons. And so there is a rule called as the octet rule, which means that most of the elements in the periodic table try to get to a stable configuration, which is the configuration of inert gases. If you look at a periodic table, the very right-hand side, you're going to see the column called inert gases or inert elements. And these are elements that do not react with anything else because they are comfortable in their electronic state. And so what that means is they have usually 8 electrons in their outermost valence shell. And so all the majority of elements are trying to get to that state where they will have the configuration of an inert element. They would like to have 8 elements in the outermost shell. The word octo means 8. So octet rule is when elements try to get to that state of stability by having 8 electrons in the outermost shell. Of course, there are exceptions. If you look at hydrogen, for example, it has only one electron in the outermost shell, but it tries to get to its nearest inert element, which is helium, and helium has two electrons in the outermost shell. So how do they do this? How do they get to either 2 for hydrogen or for 8 for, let's say, for example, here we have carbon. Carbon has 6 electrons in its various shells. In the outermost shell, the valence electron, you have 4. And it needs 4 more to get to that state. And so how do they get to that state of stability? They do this by either, again, as we saw, sharing of electrons, or giving and taking electrons, so that they come to that stable electronic configuration. So when atoms share electrons, we call this as covalent bonds. Here we have a chlorine. Chlorine has, we have 7 electrons in the outermost shell, and we have another chlorine atom which has 7 electrons in the outermost shell. An easy way they can come to that octet stability is by sharing 1 electron from each. So this chlorine is giving 1 electron, and this chlorine is giving another electron, and together now they are sharing that electron, and both of them are happy. And so think of another example here. We have hydrogen chloride. Hydrogen chloride is HCl. So you have hydrogen, which has 1 electron in its outermost shell, and chlorine, which has 7 electrons in its outermost shell. And they decide to share an electron. Now, that's again a win-win for both of them, because now they have, hydrogen has got 2 and it's in a stable state, and chlorine has got 8 in its outermost shell and it's in a stable state. And then, so both of these are examples of covalent bonds. So covalent bond, very simply, is shared electrons. Okay. Ionic bonds is when an atom decides to give away an electron, and another atom decides to accept that electron. So here we have an example of sodium chloride. As you know, it's common salt. Common salt is, so sodium has 1 electron in its outermost shell, and we have chlorine, which has 7 valence electrons. Now, sodium decides to give instead of sharing. It's easy for sodium to just give away its electron, and for chlorine to accept that electron. And so remember that electrons are negatively charged. When something gives away an electron, it becomes positively charged. So you have sodium, which now suddenly has gotten a positive charge. And then you have chlorine, which has received electron, and when it's received a negative charge, now it's gained a net negative charge. So the positive, and one of the fundamental rules in chemistry is that positive and negative will always attract. So you have a positively charged ion. Once it gives an electron, it becomes positively charged, or negatively charged. It's called an ion, right? So a positively charged ion, which is sodium, interacts with a negatively charged chloride ion, and they are held together by that force of attraction between positive and negative. That is called as an ionic bond, because 2 ions are interacting with each other. Now, one of the fundamental things we need to see, and this is a critical biological characteristic that we need to remember. Look at chlorine. How the way it is sharing its electrons. You have chlorine here, you have chlorine here. There is a property called electronegativity, which is the ability to attract electrons. So if you think of the nucleus of a chlorine atom, you have so many number of protons, and this chlorine atom also has the same number of protons. So both of them have the same electronegativity, which is the same ability to attract electrons towards itself. And so when they share an electron, they are being pulled, these shared electrons are being pulled equally on both sides. So as a result, these electrons kind of end up being in the center. And therefore, there is no charge distribution on either side, because they are now sharing the electron in the middle. So this kind of a situation where electrons are equally shared between 2 atoms is called as a non-polar covalent bond. Okay, it's still sharing, but sharing equally. But what about HCl? So you have chlorine, which has got a huge electronegativity, because think of the number of protons that are present in chlorine as opposed to hydrogen, which simply has 1 proton in its nucleus. So as a result, chlorine is has a much more stronger ability to attract electrons towards itself. So the electrons, even though they are shared, they are unequally shared. So meaning that the electrons are now closer towards chlorine compared to hydrogen. And what that means is chlorine has acquired a slightly negative charge. Remember, where there's more electrons present, there's a negative charge present. So they're still sharing, but there's a slightly negative charge in the side where chlorine is. And hydrogen, because it is kind of, the electrons are further away from it, it's got a slightly positive charge. So you represent these charges as delta, these slight positive and negative charges as delta plus and delta minus. So you have unequal sharing of electrons, which causes partial charges on atoms. This kind of a bond is called as a polar covalent bond. Why is this important in biology? See, when you have charge, charge attracts charge. Okay, positive charge, negative charge gets attracted to each other. You have positive charge, repelling each other, negative, negative repels. But when you have no charge, which is a non-polar situation, coming together, coming in proximity to a polar molecule, they don't interact with each other. So polar molecules and non-polar molecules do not interact with each other. And this determines a lot of biological properties, especially when you're thinking about cell membranes, which we'll study later in great detail. You'll see that this ability for polar molecules and non-polar molecules to not interact with each other becomes a big biological property that defines life. And also polar molecules, because of their slight negative charge here and slight negative charge here and slight positive charge here, when they come into contact with ions, let's say sodium ion or a chloride ion, they interact with them very, very nicely. So polar molecules can interact with other polar molecules, and polar molecules can interact with ions, but polar molecules and non-polar molecules do not work with each other. But non-polar molecules can dissolve together, but they don't stick together because there is no attraction between the non-polar molecules. But they are not kind of avoiding each other, if that makes sense. So let's look at water. Water has a central oxygen and 2 hydrogen atoms. And you can see this is a polar molecule. Why? Because oxygen is a much more electronegative atom compared to, has much more electronegativity compared to hydrogen. It's a very large molecule compared to hydrogen. So oxygen is now pulling the electrons towards itself from the hydrogen, even though they are shared, and the same with this hydrogen as well. So what that means is oxygen has slightly a partial negative charge, and these 2 hydrogens have slight or partial positive charges. So water is a polar molecule. Now, if I have a bunch of water molecules in close proximity to each other, what happens? I have one water molecule here, and I have another water molecule here, and you can see that the electronegative, the partial charge of the oxygen here interacts with this partial positive charge of the hydrogen from another water molecule. That attraction holds the water molecules together, and that's called hydrogen bonding. And hydrogen bonding becomes the fundamental reason for, again, not just the properties of life or life itself, but how our planet functions, why things evaporate, how the oceans run. All of these things are determined because of this fundamental property called hydrogen bonding. And so here you can see that there is covalent bond that's formed between oxygen and the hydrogen of one molecule, or one water molecule, and hydrogen bond is the bond that forms between the partial charges of different water molecules, okay, between different water molecules. So some of the properties that the hydrogen bonds create. The first one is cohesion and adhesion. You take a drop of water, okay, you take a little bit of water and drop it on wax. You'll see that water kind of clumps together in the form of a little sphere, right? Like a spherical, almost spherical structure. Why is that? It's because the hydrogen bonds, you can see within the water molecule, they are all connecting and pulling each other, right? So pulling all the water molecules together so that it kind of clumps into this space, into the shape. And sphere is the most surface area to volume relationship wise, the most favorable format to form. So that's why it forms a spherical droplet. This property of water molecules to attract to each other is called as cohesion. Cohesion is the attractive forces between water molecules. But when you place it on a surface, it's not just falling off, it is still sticking to the surface. For example, if you look at a plant, and we'll take a view of this in a second, but you'll see if take a plant, one of the fundamental reasons why water is able to transport itself from the roots to the tip of the plant, even if it's a very tall tree, the reason why it's able to go from the root to the top is because of cohesion, where the water molecules are attracted to each other, but also because of a property called adhesion, which is the ability to stick to other surfaces. So in the case of a plant, these tubes called xylem that transport water, the water molecule is able to adhere to the surface of those tubes, and using cohesion and adhesion together, they are able to move up the surface. So adhesion is the force that attracts water molecules to other surfaces. Okay, so cohesion and adhesion, you should be able to differentiate. Okay, so here's a picture of a insect, a water glider that is stepped on water. Instead of sinking, if you throw a stone on a surface, it will sink. But here, this insect is actually walking on water. Try another experiment. Take a tissue paper, put a needle on it, and place that gently on a water surface. Right. After a while, the tissue paper is going to sink, but the needle is going to float. Why is that? What is it that supports the needle? The density of the needle is higher than that of water. Why is it not sinking then? It's because, again, of the hydrogen bonds. If you look at the top surface of the water, that all of those hydrogen bonds are creating a layer of water molecules almost meshed into each other, so that the collective hydrogen bonds on the surface create a surface which is able to support a little bit of weight, including the specialized structures that you see on the ends of the feet of this water glider. So this property is called a surface tension. Okay, so surface tension. So we looked at so far cohesion, adhesion, and surface tension. I mentioned this before. So you have a plant here. You have your roots where you have water coming in, and you have these really tall trees, and the water has to go from here to the top. So if you look at a leaf, leaves have these small holes called stoma, and when water evaporates from the stoma, it creates a negative pressure at the bottom. So what it does is it causes water to kind of string all the way in from the tube that transports it, called the xylem, and it causes the water molecules to kind of string their way from the bottom to the top. And the forces that attach this water molecule to the next water molecule to the next water molecule, that is cohesion. But you also need the force where it needs to glide on the surface of the xylem tube, and that is cohesion, where water molecule is attached or attracted to the surface of another molecule other than water, some molecule other than water. So cohesion and adhesion is what allows water to be transported through these tubes all the way to the plant tip. Okay, so this is again one of the you see one of the ways that how a chemical property translates into a biological necessity. Another characteristic of water is its high specific heat capacity, or specific heat. What is specific heat? It is the energy that is required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. So all substances need, so if let's say you have some liquid, right, and you're applying some heat to it, and you keep measuring the temperature. When you apply a certain amount of heat for a certain volume of that liquid, the temperature of that liquid is going to raise by 1 degree Celsius. So what's the amount of heat you need to apply? That's the specific heat, or specific heat capacity. Water has an unusually high specific heat capacity. Why? Once again, because of hydrogen bonds. There is a lot of hydrogen bonds that are connecting all of these together. So it is going to take a significant amount of heat to break these hydrogen bonds and raise the overall temperature of water. Okay, so there's one more capacity which is very closely related to this, which is called the latent heat of vaporization of water, which is the so water, as you know, exists in at least 3 phases, right? You know, ice, and you have so the solid phase, which is ice, the liquid phase, which is water, and the gaseous phase, which is steam, and then there's plasma. But you have a high temperature, high amount of energy that you need to heat the ice to make it into water. And you need a high amount of energy to convert the so you have so much energy you need to make it into water, and then so much of energy you need to apply to convert that water into steam. So the phase change requires a lot of heat energy. So latent heat of vaporization is the amount of heat you need to convert a 1 gram of water from its water phase, from its liquid phase, to its steam phase without changing its temperature. And again, once again, this is because of the enormous amount of hydrogen bonds that needs to be broken so that a phase change can happen. So biologically, why is this important? So think of sweating. If you're on a hot day, you're walking and you start sweating. And the sweat serves a biological purpose in cooling your body. How? It takes, so the water in your sweat, it needs to evaporate, right? And where does that heat required for its vaporization come? It comes from the surrounding tissue in your body, in the skin. So it's taking the heat from your skin so that it can evaporate and become steam. In the process, because it has taken out all the heat from your skin is now cooled down. Okay, so that's again one of the reasons, one of the beautiful applications of how a chemical property translates into a biological characteristic. And one final thing we want to look at here is that water acts as a universal solvent. So we mentioned before here when we were looking at this, we said that polar molecules can interact with ions, right? So sodium chloride, think of sodium chloride, we have NaCl, and you have sodium and chlorine, because they have ionic attractions going on between them, they have formed a crystal structure here. As soon as you drop a crystal of sodium chloride in water, what happens is the water molecules, the partial charge in oxygen, for example, it all comes together around the positive charge of that sodium ion. And the partial positive charge of hydrogen in water surrounds the chloride ion, which is negatively charged. And in that process, it has broken down the crystal lattice, or the crystal-like structure that has made the sodium chloride or the salt crystal. So the crystal is broken. So water is able to do this for a lot of materials, right? And that's why it's able to dissolve. That's what we call as dissolving something, right? So in this case, you can call this sodium chloride as the solute, and water becomes the solvent, and this material that is formed is called as the solution. Okay, where water molecules surround the ions that are created by separating out the sodium and chloride parts. So water is considered as a universal solvent. So just a quick note, water there is no life without water, at least as we see it on Earth. So 60% of our body is made of water, and of that 60%, most of it is found inside the cell, in the cytoplasm. Your cytoplasm is mostly water. And 33% of that is made of extracellular fluid, which is the liquid found outside the cells. And some of that is present as blood plasma, and some of that is present as interstitial fluid, which is the fluid that is present in, as lymph fluid and cerebrospinal fluid, and the fluid that makes up your tears and your synovial fluids and all of that stuff. So to summarize, properties of water that define life on Earth: water is a universal solvent, water has high surface tension and high heat capacity, a specific heat capacity, high latent heat of vaporization. One property which I didn't talk about here, and this is really important, is that water as a solid has less density than that of its liquid. Usually this is the other way around. Most liquids have less density than solids. But water is the opposite. Why is that? So let's take a look at this here, right? So imagine if this was a liquid. You have all of these bonds that are forming between the partial positive and negative charges, and these bonds are constantly being broken and recreated and these water molecules keep sliding on top of each other. Because of that, you're able to pack a lot of water molecules within a small space. But when you reduce the temperature, these molecules are not able to freely move around. So what that means is water molecules are stretched to the length of their hydrogen bonds, and then there is no more energy for them to move around. So there is less density, less tightly packed compared to that of liquids. And because of that, solids of water, which is ice, has less density than that of liquid water. And I think that's a very important biological characteristic. Let me tell you why. So think of a lake, okay, and you have a very very cold winter, and imagine if water was more dense. I'm sorry, ice was more dense than water, and the ice will first sink to the bottom, right? And if ice sinks to the bottom, then slowly as the cold temperature continues, more and more ice accumulates from the bottom of the lake all the way to the top. And what that means is if there was any life on this thing, if there was any fish, everything is going to die. But because ice is less dense than water, the first layer of ice that forms is on the top. What that means is it acts as an insulating barrier so that the water underneath is not, it doesn't cool up, it doesn't freeze. And so that's a critical element of how or why life exists on our earth in water. Of course, when we saw that we have adhesion and cohesion properties, and then there is a concept which again very very critical when we study transport of molecules across cell membranes and things like that, is hydrophobic and hydrophilic. So the word phobic means phobia, right? So hydro means water. Hydrophobic means fear of water. It's not afraid of water, it just doesn't interact with water. Philic means love, right? Philadelphia, city of brotherly love, right? So hydrophilic means love of water, meaning that it's able to interact with water. So we have molecules, and you can imagine that polar molecules would be hydrophilic, ions are hydrophilic, and non-polar molecules will be hydrophobic. So we have biological molecules that are hydrophobic that will not interact with water, and we have biological molecules that are hydrophilic that will interact with water. Okay, so just again a quick note on how water becomes important for us. Everything from saliva in your mouth, to how your urine is secreted out, to how your joints are lubricated, to how blood delivers oxygen to all over your body, to transmitting neurotransmitters through blood. Everything depends on water. Okay. All right. One last concept, and then we'll end this chapter. This is the idea of pH. Now, you've probably seen this before, heard this before, but pH means the power of hydrogen. So P is, this lower P is for power of hydrogen. It's a measure of the amount of hydrogen ion in a solution. So if you have more hydrogen ions, then you have less pH. And the more hydrogen ions a solution has, then it is more acidic. If you have less hydrogen ions, then you have more pH. Okay, and then it is the more pH there is, the more basic or alkaline that solution is. So the pH scale is typically from the standard scale is between 1 and 14, and smack in the middle at a pH 7 is considered as neutral. So pure water would be a pH of 7. Our blood is slightly alkaline. It's 7.35, I think, somewhere around 7.3 to 7.35. And so if you have things like ammonia and bleach and sodium hydroxide, they are all very alkaline solutions. And if you have hydrochloric acid and lead battery and there's acid in your stomach, which is extremely acidic, all of these are low on the pH scale. So why is it negative? I'm sorry. Why is the pH going in the opposite direction? It's because of the formula you calculate. How you calculate pH? pH is the negative logarithm of H plus, which is the hydrogen ion concentration. Okay. Anyway, we'll study this later again when in a different unit. All right. So I just want you to. So those are all the things I wanted to talk about. The different properties of water. We studied chemical bonds. We looked at polar versus non-polar molecules. We looked at hydrophobic and hydrophilic, what that means. And we looked at how the properties of water, cohesion, adhesion, specific heat, latent heat of vaporization, surface tension, all of these are determined by the hydrogen bond nature, bonds of water. And finally, we had a quick introduction to pH. Okay. Hopefully this helps. So in the next chapter, we are going to look at the different elements that make up biological molecules. All right. Thank you.